Hello.
Hello?
Hi. Hello.
Can you hear me okay?
Yep.
Fantastic. How's your day coming along?
It's pretty good, pretty busy. How about yours?
Same. Pretty
That's
busy, but
always good.
yep, busy is good. So I'm sorry about the inconsistency with lessons. There's been a lot going on in my life the past month or so, and I know that's not a good excuse, but I really appreciate you working.
No, no, that's same here. I've had to cancel quite a bit, but summer is just when you're older, I guess it gets busier.
Yep, exactly. I miss summers of just cartoons and climbing trees, don't you?
Yeah. Yeah, those
Those
were
were
the
the
days.
days, the golden days. Yes, indeed.
Yep.
So we are continuing on with integration techniques. It's probably the most important thing we're going to be learning in this class, not only using the techniques themselves, but also identifying circumstances in which we use certain techniques. So the goal of this class is for you to be able to look at any integral and just tell right away, oh, I need to use u sub, or I need to do a trig substitution, or something like that. So we want to get really, really good at that before we move on to infinite series. So do you
Uh-huh.
have anything you want to ask questions about? Anything that requires clarification so far? Anything at all?
Nope.
All right. So I guess we want to just continue practicing. I want to give you some integrals, and then I want you to kind of talk me through it as far as the techniques we want to use and why.
All
So
right.
let's see if you remember how to integrate the natural log function. What do we want to do here?
Well, I mean, I know the rule, so the natural log function, it into integrating it. Oh wait, no, this is integrating it. Um, we have to find a way to rewrite it in order to maybe use u sub or something else that can help us because you can't really integrate the natural log function on its
You
own.
are correct. Yep. So if it were natural log of x over x, we could use u sub. This is a direct u sub situation because we have u
Mm-hmm.
to be natural log of x, and then the derivative would be 1 over x. But we don't have that. So we actually want to use integration by parts in this one. So can you show me how to set that problem up? Can you write it on the board? Here, in case you don't
Yep.
remember the formula, let me just sketch that up at the top. So integration by parts tells us that whenever we have the integral of the product, u times dv, the product of two different functions, it's going to be uv, u times the antiderivative of dv, minus the integral of v times the derivative of our function u. So remember, we have to be really clever in picking a u and picking a dv. Do you remember what the strategy is for deciding u and deciding dv?
Um, I believe dv is the term that gets simpler the more you differentiate it, and then whatever else is left is your u.
Actually, we want u to be simpler when we take the derivative. We know that because if we have u here, we have du right there. If we set natural log of x to be u, that won't really work. Or actually, hang on. Sorry, I got ahead of myself there. If we make natural log of x dv, that wouldn't really work because if we look at the formula, we have to take the antiderivative of v. We have to take the antiderivative of dv, excuse me. And we don't know what the antiderivative of natural log is quite yet. So that's not a very good choice for dv.
Mm-hmm.
So you can think of it as you want u to be the function that gets simpler when you take the derivative, or you can think of it as you want dv to be the thing that you can take the antiderivative of, because ultimately we have to take the derivative of u. And ultimately, we have to take the antiderivative of dv. So we can't take the antiderivative of the natural log just yet. So that means we can't have that be dv. So I want to see if you can write on the board, see if you can write a definition for u, for dv, and then find v and du to go along with those.
All right.
You should have permission to use the board. Let me know if you don't have permission.
I do.
Fantastic. All right, looks good. So what's u in this case?
Uh, I think it's gonna be I want to say natural log of x. I want to.
Exactly. That's a really good choice for you because we know what the derivative of that is. We just don't know what the antiderivative is yet. So that's why it's a good choice for you and not a good choice for DV. So then what's
Okay.
DV going to be in that case?
It's gonna be everything else, so it's just gonna be dx.
Perfect. So now that we have that information, we want to find du. How do we find du?
We just differentiate. So
Mm-hmm. And don't forget the differential. We're also going to have a dx be part of that. Do you remember where the dx comes from?
when you take the derivative of anything, you just write it as like dy over dx, right? But in this case, we have it'd be a du over dx. So then we just move the dx instead of the denominator on the left side as a denominator on the left side of the equation, just a constant or not a constant, but
The
um,
differential. Yep, absolutely.
yeah,
Want to
it's a
move the
differential.
differential to the other side. Perfect. And then what about v? How do we go from having a dv to having just a v?
Well,
What's the antiderivative of v?
it well, it's just gonna be x
Perfect.
basically. So
So now we have
um,
everything. Go ahead and plug everything in. So we're going to have uv, no calculus involved right here, just simple substitution. This part is where the calculus comes into play. Are you using a writing tablet?
no, my mouse.
Your handwriting is really impressive for using a mouse.
I don't know. Maybe I'm just gotten used to it over time.
I wish I did. This is my fifth time teaching calculus on, well, I guess the first time I taught it in person, but then I started teaching online since COVID hit. This is my fourth time teaching calculus online, and my handwriting still isn't very good. And
I mean,
little
I'd say it's pretty good.
I appreciate that, but little kids are brutally honest. That's always the first thing they say. I mean, I appreciate the honesty, but after a while, it's just ouch.
No,
So,
as long as it's readable, I don't think it really matters.
all right, I appreciate that answer. So, how do we move? How do we go on from here? So we have something. We don't need to do anything with this middle term anymore. That part is completely done. How do we integrate the second part?
Um, well, I think, uh, I mean, we just simplify and then, when you so dx is basically saying the derivative of x. So when you integrate anything that's, when it's being, when you're deriving it, the integral and the derivative cancel each other out. So it's just going to be x.
Well, let's simplify first. Let's forget about the integral and forget about the differential. What do we get when we simplify x times 1 over x?
One
Exactly. So we're going to take the antiderivative of just dx, and what do we get?
x.
Perfect. So at first glance, it doesn't even really seem like that good of a strategy, right? Because we started with an integral, and then we ended with an integral. How did that help us at all? So why is it better to have this right here instead of this? How is this useful?
Well, I mean, the red shows us that that you can take the integral of it first and foremost. When you look at the integral of just a natural log of x dx, your first thought is you can't really integrate that. If it was maybe 1 over x dx, then you could, and it would turn out to be ln of x. So uh, integrating by parts shows that it actually can be done, and we rewrite it in a way that makes it in this case, it's simplified very well. So
Fantastic. Yeah, it's a common theme of this course, breaking up big problems into small, manageable problems. So we may not know exactly what to do here, but we do know exactly how to integrate this. This is something we're used to. So that's why it's such a powerful tool, such a powerful strategy. It's something called modularity, being able to break up a huge problem into small, manageable pieces. So that's the goal. So we want to become really good at identifying situations where we can use this, situations in which it is helpful and effective for our purposes. So let's see if you can see if you can write the final answer for us underneath what you already have written in. Excellent. And we know we did that right because if we take the derivative of this using the product rule, we're going to have the derivative of the first times the second plus the first times the derivative of the second. And then, of course, the derivative of a constant is just 0. And then we get exactly what we started with. Fantastic. Good work. So let's
Thank
make
you.
a small modification to this. What happens if we have x natural log of x? What do we want to do in this situation? What kind of a strategy would be helpful?
Um, well, I mean, we could mess around with it at first to see what would be a good way to approach it. But
Right, exactly. So there are going to be some situations where we want to simplify before we integrate. That's most common when we're dealing with trig integrals. And then there are going to be situations where we just want to dive right into the calculus, dive right into u sub or integration by parts. So out of everything we learn in this class, what kind of a strategy would be useful? It's okay, just think about it for a few minutes. See if you can think about everything we've learned in this class and then see if you can work out the best way to tackle this. Keeping in mind that we have a product here. We have this x times something else. Do we know anything really useful for integrating products?
yeah, I would say integration by parts again.
Exactly. So show me how to work that part out. Oh, and by the way, I am recording this as you requested.
Yeah, yeah. Um, well, first we're gonna need a u and a dv.
Mhm.
You want u to get simpler as you derive it more and more, and dv to be everything else.
Right.
So
This one is a little tricky because natural log of x does kind of get simpler when we take the derivative. We go from having a logarithm to having just 1 over x. That gets simpler. And then also if we take the derivative of x, we get just 1. So I'm curious to see which one you choose to be u and which one you choose to be dv.
honestly, I want to choose both.
Well, give it a try, see if it'll work.
All right.
Learn by doing is one of the goals of this class. Oh, and do you need the formula again?
No, I wrote it down.
Perfect.
It's minus the integral of v du, right?
Mm-hmm.
All right. 'Cause I wrote v here.
Excuse me 1 second.
Mhm. Oh,
Sorry about that. That's really unprofessional. I apologize for that.
you're good. No, I'm just working on I'm about to finish this up. I forgot for a second what I needed to do, but I remember. So,
So we have a u. What do you have for du?
um, I'm taking the derivative of u, and I said to just use the product rule
Hmm,
after, remembering that that exists. So I'm currently doing that right now.
Perfect. Looks excellent.
And now,
But this one looks really interesting because look what happens if you break this up into two separate integrals. So we have the derivative, the integral of x times natural log of x. And if we distribute the x to the one, we're going to have just the integral of x. So notice we have the same thing here as we have there. So this probably
mhm.
wouldn't be my first choice of method, but I want you to carry it out like this because it's going to show you something really, really interesting that's actually going to come into play a little later on in this class. So you're doing a great job so far. Keep up the good work.
Don't we just keep doing it, I think?
Well, notice how we already have this written in some form. So we have this is also being this, it's also present right here. So we have positive integral x natural log of x, and then right there we have negative integral x natural log of x. Is there anything that can be done to simplify this? Does anything kind of jump out at you about what to do here?
I mean, I can move the black square on the outside and then make two integral of x ln x dx.
Yes, exactly. Exactly what you want to do. So yeah, go ahead and do that here. I am most accomplished in the art of laziness, so let me help you with that. Perfect.
Nice.
I call that Polish efficiency.
Polish?
Yep,
How why Polish?
because I'm Polish, and
Mm.
yeah,
If you think about it, it's just efficiency,
I guess you're right.
really.
No need to bring ethnicity into the mix here. So, oh, never mind. I see. Perfect.
Okay, I think that's it. Oh, wait, no. Plus.
And we do need to have a constant there. So one thing I noticed right away is that you forgot to distribute this x right here to this positive 1. So this part right here should
Oh,
not be the integral of 1. It should actually be the integral of x.
yeah. Let me change that.
So I don't know what other people call this method, but I call this the recursive method because recursive, when a function is recursive, it means you use the function itself when you are trying to carry out its operations. Kind of like in computer science, I don't know if you've done any programming, but when your computer calls a function and it uses itself, we call that recursivity. So,
Hmm.
yeah, perfect. Yeah, it looks like you got
Oh,
that part right. 1 negative 1 half x squared. And then that changes the answer, the final answer, of course.
oh, wait a minute. I can just do.
You can break it up into multiple terms if you like, if that makes it a little bit easier for you.
Oh, I think that's it right there.
Yeah, perfect. Very nice. So are there other ways we could have done that, do you think?
Um,
So using
I don't
integration by
know.
parts, what would happen if we set this part, oh, hang on a second, let's rewrite this real quick. So this isn't completely necessary. This is just me being OCD. What happens if we put the natural log first and then the x second? And what happens if we call this part dv and we call this part u? Would that make it easier, um, more difficult, or nothing at all? What do you think? How do you think that affects the outcome
Off
using
the
these two definitions?
off the top of my head, I have no clue how that might affect it.
Let's try it because this is one of those really rare cases where you can choose either the recursive method, which is what you've just done, or we can use a different method. And it is really rare. Oftentimes you have to use the recursive method. And we're going to be getting into examples in which you have to do that a little bit later. But as of now, we do have a choice. So I want you to try it again using this u and using this dv, and then see which method you prefer, the recursive method or this other method.
All right.
This is helping us with our goal of being able to take a look at an integral and then deciding what method would be the most efficient.
Yeah, yeah, that's the goal.
Or hang on a second. So this should be uv minus the integral of v du. So du would be dx over x,
Oh,
and
right.
then v would be the antiderivative of x, which would be 1 half x squared if we use that integration power rule.
That's true.
So try that part again.
Do I still need a dx though? Because if I have the dx on the second term,
So where is the dx on the second term?
I mean in the integral, this one right here.
So this is integral of uv minus the integral of v times du. So the integral comes only from the du. So if du wasn't here, you wouldn't have the differential. So you definitely do need that there. So are you trying to ask if we need to add a different dx in addition to the one you've already written as part of du?
Yeah, yeah, like how you always have one in, or
Nope.
if the
That's the nice
first
thing.
one is.
Sorry to interrupt you, but that's the
No,
nice
no,
thing
that's
about
fine.
this. That's the thing that really makes sense about this technique. This gives us the only differential we need. We don't need to put another one
All right, sweet.
there.
That's good.
Indeed.
So,
And we're only doing an hour today. Is that correct?
yeah, but honestly, I mean, I probably, yeah, I could go for longer if you'd like to.
Well, it's not necessary. Like I said, there is no deadline for this course, which is really nice. So I understand you have other things to do. If you can only do 1 hour today, that's perfectly fine. But then what is your schedule like tomorrow?
Tomorrow I have to go to work. That's why, so because tonight I'm gonna be finishing up my course pretty much. I mean, everything for a final. So,
So I don't know if you're willing to do some of this on a work day. Is it possible to have class tomorrow, like tomorrow before or after work? I don't know if you're like too put out.
after work I can get home around 7:30 and then we could probably do it.
All right, perfect.
Okay.
Yeah, I'll text you about that tomorrow. Sounds good?
Yep.
Perfect.
All right. I'm gonna say that's it.
All right, yeah, looks perfect. And if we simplify it, you can see we get the answer we started with, or we not started with. We get that same answer we did using the recursive method. So out of these two methods, which one do you prefer? What do you think is the most effective?
Um, I don't know. I feel like this one is a little more it sticks a little more to the formula, which may be good.
Yeah. So like I said, the recursive method comes up in situations where you have to use that one. So in situations like this where you have a choice, it is better to use the other one. It is just a little bit faster. There's less algebra, there's less busy arithmetic work to do. So it is nice to do it this way if you have that option. All right, good work. Let's say you have something like this. Let's say we have x over 1 plus x squared dx. Now, how do we integrate something like this?
I think this one's gonna be u sub.
Yeah, Perfect. What kind of just gave it away that this is a U sub problem?
I don't know. I feel like I've done this one before and it was use of. But if I look at it, you take the derivative of actually, I don't know. Yeah, I feel like I've done a type like this before and it was U sub, so that's why I said it. But if you
Right?
take the derivative of the denominator, you can get pretty close to the numerator.
Yeah, exactly. So U would just be 1 over x. Take the derivative, we get 2x dx, and then divide both sides of the differential equation by 2, and then you would have 1/2 du over u, and then we'd get 1/2 natural log of u. But then what happens if we don't have an x upstairs? What if we have just 1? We can't really do u sub because the derivative we have downstairs is unchanged. The derivative is still going to be 2x, but we don't have an x above to take care of that part. So what does this make you want to do? Besides pull your hair out and scream.
Um, maybe an integration by parts.
All
Well,
right.
actually, yeah, maybe that might work.
I'm not going to give anything away. It may not. So, just for the sake of argument, what would you choose to be u, and what would you choose to be d?
I would, hmm, I would choose u to be either the entire fraction or just the numerator denominator, and then the rest would be a dv.
That
But
would get pretty complicated because if we set u to be
yeah,
the entire fraction, we'd have to do the quotient rule for integration, or sorry, for derivatives, and the denominator would be the square of
squared.
quantity
So
1 plus x squared, and it's a bit complicated. I mean, it might work, but a lot of tears would be shed, a lot of frustration would happen. We'd probably just succumb to Wolfram Alpha to help us with that one. So we're going to be using a different technique. And I think we did talk about this a little bit in Calc BC. We're going to use a different kind of a substitution for this one, not a U substitution. We're going to use a substitution like this one right here. So let's set x to be equal to tangent of theta. Now, this is one of those problems where it doesn't look like anything trig related is involved at all. We're used to seeing sine and cosine and tangent in the integrand. We're used to seeing limits that are in terms of pi. So at first glance, it doesn't look like anything that's trig related whatsoever, but it actually works out really nicely and really beautifully to use trig to help us with this one. So
okay.
let's say x is equal to tangent of theta. Well, we don't have just an x. We actually have an x squared. So what I want to do is I want to square x in order to find a suitable replacement for the thing I drew a box around. So x squared is going to be tangent squared theta. So let's take the derivative of x with respect to theta. So if x is tangent of theta, what is the derivative of tangent?
I think
The derivative of tangent is secant squared of theta.
secant. Okay, so then it's gonna be oh wait, there's oh okay.
So then we want to do what we do with the U substitution. We're going to multiply both sides by the other differential. So we get secant squared theta d theta is equal to dx. So now let's substitute everything in. So we're going to have an integral, and I'm just going to move the dx up front just to make things a little bit more condensed, I guess, if that's even the right word. So I'm going to replace dx with secant squared theta d theta. That's going to be our new denominator, or numerator, I meant to say, sorry. Secant squared theta, and then d theta is going to go right here. And then downstairs, we have not 1 plus x squared, but 1 plus tangent of theta, 1 plus tangent squared theta. So why do you think it's preferable to have this instead of the form that we started with? Do you see any advantages to rewriting it like this?
Yes.
What would that be? Why is this preferable to what we
Um,
started with?
there's that one. What do you call it? There's this one identity that we pretty much have on the bottom. that will
Exactly.
allow us to just, I'm trying to think, I don't entirely remember it, but is
Yeah, this would be a good time to pull out that trig identity table if you have one.
okay. The reason why we want this is because 1 plus tan squared theta uh, is equal to secant squared theta. So the whole fraction is equal to 1 really. And when you have to integrate d theta, you just get theta.
Perfect. No need to finish that. Let's try another one of this type though. Let's try the integral of square root quantity 9 minus x squared. All divided by x squared dx. So this is another trig substitution problem. So we have a few different choices of substitutions we can use. We can use x equals a times sine of theta. I'm going to put the theta a little bit later, or we can do a tangent of theta, or we can do a secant of theta. So tangent worked really well in the last one, and the reason why that is because tangent squared theta plus 1 gets us cosecant. And we had that 1 there, we had the minus 1 there to help us out. So look what we have upstairs. We have 9 minus x squared. So can you think of any trig identity that has something that looks maybe remotely like this? Imagine the 9 is just a 1. Can you think of a trig identity that would help us integrate, or sorry, help us rewrite this so that it simplifies a little bit nicely? One of the Pythagoreans.
The Pythagoreans.
One of the Pythagorean identities. Kind of like the one we used last time. Remember that last time we had tangent squared theta plus 1 is secant squared theta. It's going to be one of those types.
So one of those three things listed will help simplify the 1 minus x squared.
Yeah, exactly. We have 2 terms. It'll be something that'll help us change 2 terms so that it's just 1 term.
What exactly is the a in this case?
Well, we're going to find out as soon as we decide on an identity. We have to choose the identity first, and then we can
Okay.
choose a value.
I think it's going to be x is equal to a tan squared.
Well, I'm thinking the identity that we want to use would be the first Pythagorean one. There's one that says sine squared theta plus cosine squared theta is 1.
Well, yeah, so we changed the 1 to sine squared theta and cosine squared theta. But then oh wait, yeah, no, the tan is not going to exactly help us out.
So if we take sine squared theta plus cosine squared theta, or in this case, x, I don't know how to make a theta with my keyboard, but if we take this identity and then if we subtract both sides by cosine squared x, we get 1 minus cosine squared x, which is really useful. This looks a lot like what we have, because if we compare this with what we have in the integral, it's pretty similar. We have a constant minus something to the second power. So that's why sine would be the one we want to use here. This is our winner. We don't want to use tangent or secant. So now that we know that this is the one we want to use, we can pick a value for a. It's going to be some constant. In the last one we used, the constant was just 1. But this time it's going to be a little bit different. And the reason we know it's going to be different is because, hang on, let me see if I can. All right, good. So the reason we know that it's not going to be just 1 for this case is because we have a 9 right there. If it were just a 1 minus x squared, a would be 1. In this case, we want to take the square root of whatever that is. So this is of the form a squared minus x squared. So whenever you have something that looks like this, an a squared minus an x squared under the radical, you want to use sine. You want to use the sine substitution for this. So then in this case, can you identify a and identify x squared? Well, actually, can you just identify a in this case?
A would just be 3, right?
Yep, perfect. So we want to use this substitution. So now that you have that, I want to see if you can find x squared and then find dx for us on the board, if you don't mind.
And dx.
Mm-hmm.
All right.
All right, perfect. So there's something we forgot in the dx. There's one more thing we need to have there.
Is it a differential?
Yes.
How how would you do that though? Just do x
We
over
started
d.
off with this.
Oh, dx in terms of theta. That's right. Okay.
Mm-hmm. We want to have that be 3 cosine of theta d theta. Perfect. Now go ahead and rewrite the integral, substituting everything in for x squared and for dx. All right. So it looks like we made things uglier and nastier, but oftentimes you have to do that in order to eventually get to something you can integrate. So we're actually on the right track here. Do you see anything we can do to simplify this further before we can even get into the integration process?
I see a 3 and a 9 that simplify.
All right, that's a good start. And then of course, so see if you can simplify that and move a constant out front of the integral if that's possible. All right, perfect. But then what about that radical? Is it possible to simplify the radical at all?
Uh, I don't think so.
Well, under the radical, I see that we have a difference of squares. How do we do a difference of squares factoring?
Oh,
Or actually, you know what? There's actually a better way. So I see that they both contain a 9. So what would happen if we were to factor out a 9 from both of those and give them 2 separate radicals? So you would have 9 under its own radical, and then you would have a radical over everything that remains after you factor out the 9. Show me what that would look like. Yeah, perfect. And now we can simplify the radical quite a bit. What do we get when we simplify the square root of the quantity 1 minus sine squared theta? Using that identity from before.
oh, which identity from before?
The Pythagorean identity involving sine and cosine. I wrote it down about 6-7 minutes ago, but then I erased it. This one right here.
Oh, that one. I mean, we could change the one into sine squared plus cosine squared, and then we have a minus sine squared. So it'd just be square root of cosine squared theta,
Yes.
which is just cosine squared theta, I guess.
Not cosine squared theta. You had it right the first
I mean,
time.
just
So
cosine theta. Just
just
cosine theta.
theta. Yep.
Okay.
Fantastic. But then what can we do with the 3?
I believe. Oh yeah, we can factor that out as well,
All
and then
right.
that'll just cancel that out.
Works out pretty nicely. And then see if you can integrate from this point on.
All right.
Excellent. So this one isn't directly, we can't integrate this one directly. So you're going to need to rewrite this using one of the trig identities and then integrate what you get as the result.
All right.
We might need a little more room. So I'm going to move this over quite a bit. All right.
I'm looking for that one little cheat sheet I had with all my notes on it. I can't seem to find it.
Do you want to pull it up on your phone?
No, I'll go it alone.
Okay.
It's actually this shouldn't be that hard.
Is there a way to share files over Zoom?
I actually, yes.
How do you do it? I have mine pulled up right now.
Just go to you click on the chat, and then if you see what I see, it'll have like on the bottom of the box, it'll say to everyone, type your message here, and then to the right, it'll have this button that says file.
The file button. Yeah, perfect. All right, I'll send that over to you. Sending right now. All right, did you get it?
I saw it.
Perfect.
Yeah.
All right. Were you able to open it successfully?
Yeah. I the one thing I'm looking for in my own cheat sheet is I wrote down how each and every trig function derives.
Oh, sorry, I didn't see this part right here. I didn't see that. So you
I added that while you were setting it, which is probably why.
Oh, so this is 100% good. So this is excellent. That's exactly what you want to do.
See, now I'm figuring that cosecant -1 is exactly what we want.
Yeah.
But I just I don't have them memorized by heart. So I'm gonna go. I'll be right back. I think I know where they are. I'll be in like a minute at most.
No problem. Take your time.
All right, I've got him.
Perfect. Fantastic. Did really well. So this is one of those beautiful things about math where you think this doesn't look anything remotely trigonometric, but it turns out
Hmm.
the answer to this is actually a trig function. So that's one of the beautiful parts of math, in my own humble opinion. You might think I'm crazy for thinking math is beautiful, but I think sometimes its beauty is hidden.
I mean, just about perspective. You could either say that this process is beautiful, or you could say it's incredible, or you could say it's just frustrating and should not even exist, but all about perspective.
You could say, this sucks. Why am I not majoring in underwater basketball?
Hmm.
All right, so let's apply this to a geometry problem. Let's say we have some ellipse given by an equation. Did I spell that right?
I think so.
All right, let's
But
say we have
man,
ellipse given by this equation. Those
I
conic
did,
sections from algebra 2 we all love so much.
I did them in, yeah, no, I did them in pre-calc as well, but I do not remember anything about them.
So this is an ellipse. We have x squared over a constant. Just in general, this is the general thing.
Yeah, yeah.
And then let's see if you can figure out how to find the area of this. But I'm going to try my own cruddy drawing of this first. It's centered at the origin, and it's going to look like crap. But this is my attempt. So we're trying to find the area of this ellipse in the first quadrant. So how would we set up the problem first? We want to set up the problem and then solve it using integration as a tool to help us find this area.
Yeah, I think we would have 4 integrals with various limits of integration.
All right, well, let's say we only care about finding the area of the first quadrant.
First quadrant. Oh, first quadrant. That'll be only one integral.
Yeah,
But
so let's only focus on this for now.
we'll have as limits of integration, we'll have a as b, and then 0 or the origin as b.
So in
That makes
3,
sense.
in calculus 3, we learn how to integrate things in terms of multiple variables. But one thing we can do first is to put everything in terms of just one variable. So how do we put everything in terms of only A or everything in terms of only B? Or sorry, I made a mistake in saying that. How do we put it in terms of only X or in terms of only Y? So A and B are just constants. Remember that. How do we put everything in terms of just Y or just X?
Oh, we set our limits of integration as x or y.
They're not going to be the limits. Remember, the limits are going to be the thing that tell us how far to go. So as far as we want to go, it should be 0 going all the way up to A. And remember, ultimately, we need something like this. Y is a function, then dx is going to be the differential part of that. So how do we go from this equation of the ellipse to something like this we know what to do with?
We'd have to manipulate the actual ellipse function to isolate one of the variables, whichever one. I don't think it matters.
Yep.
And then for example, once we find what x squared is by isolating it from y, then we can just substitute whatever it's equal to, and then we have everything in terms of y.
Well, how about you put y as the variable? How about you put it as y equals something? Because that's just what we're used to. We're used to having integrals in terms of x with dx as the differential. So how about
Okay.
how about you just set it as y equals something? Solve for y.
Okay, I'm pretty sure that's right. So we have y. I think we just keep it as y squared though, since we're trying to integrate the ellipse function, the original function.
So let's see here. So we have y squared over b squared, and then I agree, we want to subtract x squared over a squared, but don't forget we still have a 1 right there.
Oh, no, okay.
We want to just
Um,
put a 1 in front, like right there. So y squared equals 1, and then you have to take the square root of this entire thing then.
yeah. Dang it. Okay. That was suspiciously worked too well.
I know, right? I hate to say it, but yeah, you're totally right.
Um, okay.
And then let's find the area of the whole thing. I will tell you that this thing is not only symmetrical about the y-axis, but also symmetrical about the x-axis, meaning that if you find this area, call it capital A, all you need to do is multiply it by a constant to get this whole thing.
Oh, okay. That's a lot. That's very comforting.
Mm-hmm. So actually, I think we started about 5 minutes after 5, so we're finished right now. I actually want to assign this one for homework if that doesn't make me too evil of a person.
No, no. I'm actually looking forward to it because I think I could do it
I'm glad. Most
pretty.
people don't say that. Most people say Justin, and they call me a bastard under their breath. But that's really refreshing.
No, no. I mean, I'm pretty sure I could do this problem. So,
All right.
might as well try it and see where it takes me. But I also, as you said, I do want to get to that point where I just, it's just like that. I know exactly what to do because, that's how I know, I've practiced enough of these problems.
We'll get there in time. Sometimes it's frustrating. There have been times where I decided I don't want to study math ever again. I want to be a history major and just remember stuff, but
Yeah,
everyone reaches that
sometimes
point.
but then I told myself, well, I mean, I already know that I don't remember anything most of the time, so I don't think a history major would, do too much good for me.
Yep. Well, my point is frustration is good because it means you're working out your brain. It's kind of like going to the gym and your muscles are sore because that's how you know they're working. When your
Yeah,
muscles are sore,
yeah.
they're growing. When you're frustrated, it means your brain is crying for you to stop, but you shouldn't stop. It means you're learning things and you're getting closer to the goal of mastering this material. So you have a really healthy attitude that a lot of people don't have. So kudos to you on that. And if you don't have any questions, you're free to go whenever you're ready. Feel free to copy this down or just take a screenshot, and I will
I
see
took a
you tomorrow.
screenshot. All
All right,
right.
fantastic. Have a wonderful evening.
Actually, I'm gonna check to make sure I took the screenshot. I don't want to, not have
Yeah,
the problem or something like that. And
good idea.
uh, I think what is today's the 24th? Yeah. Yeah.
Yeah.
Okay. I've got it. I've got it.
All
All
right.
right.
Have a
Sounds good.
wonderful
I'm sorry.
have a wonderful evening.
All right. Thank you. You too. See you next time.
See you tomorrow.
Yep. All right.